March 14, 1942. HMS Orchis, North Atlantic convoy route. The oscilloscope screen flickered with a return that should not have existed. Lieutenant Commander David Milner stared at the green phosphor trace, watching the echo pulse at precisely 8.3 miles range, bearing 047 degrees true. His hands moved across the Type 271 radar controls, with practiced precision, adjusting gain and tuning to eliminate any possibility of equipment malfunction or atmospheric interference. The return remained steady, clear, unmistakable. A submarine conning tower, detected at a distance that every technical manual and every radar expert in the Royal Navy had declared categorically impossible just 6 months earlier. The German U-boat commander running on the surface through pre-dawn darkness believed himself invisible. He was following doctrine, surfacing at night to recharge batteries, and transit at higher speed toward the convoy's projected position. His Metox radar detector remained silent because HMS Orchis operated at a wavelength the German equipment could not sense. The U-boat's lookouts scanned darkness that human eyes could not penetrate. They saw nothing. They suspected nothing. They had no idea they had been under continuous observation for the past 11 minutes. Milner reached for the voice pipe connecting the radar office to the bridge. "Captain, radar contact, classified submarine, range 8 miles, bearing 047, contact is steady and tracking." The words were routine, spoken hundreds of times during convoy escort duty, but the implications were revolutionary. For the first time in naval history, a surface ship had detected a submarine at a range that provided enough time to close to attack position, coordinate with other escorts, and execute a killing approach before the U-boat could dive or escape. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. What Milner could not know as HMS Orchis altered course to intercept was that the radar set guiding him toward that U-boat represented the culmination of a technological revolution that had nearly failed before it began. The Type 271 radar that painted submarine contacts at 8 miles had not emerged from university laboratories or government research programs. It had been saved from cancellation and transformed from laboratory curiosity into war-winning weapon by a civilian electrical engineer whose name would never appear in official histories. Frederick Edward Jones had looked at a radar circuit that every credentialed physicist insisted could not work, recognized why it failed, and redesigned it using principles so unconventional that Royal Navy technical reviewers initially rejected his modifications as theoretically unsound. He had been proven right, not through mathematical proofs or published papers, but through sea trials that demonstrated detection ranges tripling what British scientists had thought possible. He had given the Royal Navy eyes that could see through darkness and weather at distances that changed the fundamental mathematics of anti-submarine warfare. But the story that deserves to be told is not simply about radar technology or circuit design. It is about how institutional resistance to unconventional thinking nearly cost Britain the Battle of the Atlantic, how a self-taught engineer working in a cramped factory laboratory solved problems that university researchers with advanced degrees could not solve, how desperation forced the Royal Navy to accept solutions from sources they would have dismissed in peacetime, and how one man's refusal to accept expert consensus about what was impossible created the technological advantage that turned convoy escorts from reactive defenders into proactive hunters. September 7, 1940, London. The Blitz had begun the previous day with 448 German bombers striking the city in waves that continued through the night. Frederick Edward Jones, 34 years old, stood in the rubble of what had been a warehouse 3 blocks from his home in South London. Fire crews were still working to control blazes that had consumed entire neighbourhoods. The smell of burning wood and chemicals hung thick in the morning air. Jones had been born in 1906 in Woolwich, southeast London, into a working-class family that could not afford university education. His father had been an electrician working in the Woolwich Arsenal, the massive government facility that manufactured artillery and ammunition. Young Frederick had grown up surrounded by machinery and electrical systems, learning through observation and apprenticeship rather than formal instruction. By age 16, he was working as an electrical technician's assistant. By 20, he had taught himself enough circuit theory and practical electronics to secure a position with a small radio manufacturer. His expertise was entirely self-acquired. He had never attended university, never studied under famous professors, never published academic papers. What he possessed instead was an intuitive understanding of how electrical circuits behaved in practice rather than theory, gained through thousands of hours of troubleshooting equipment that did not work according to specification. This practical knowledge, dismissed by academics as mere technical skill rather than true engineering insight, would prove more valuable than any theoretical training could provide. By 1940, Jones was employed as senior electronics engineer at Metropolitan Vickers Electrical Company, one of Britain's largest electrical manufacturing firms. The company, known universally as Metrovic, had been founded in 1899 and had grown into a major producer of electrical equipment, railway locomotives, and industrial machinery. When war began in September 1939, Metrovic, like every major British industrial concern, had shifted to military production. Jones's division was assigned to radar development, specifically the Navy's requirements for ship-based detection systems that could locate enemy vessels beyond visual range. The technical challenges were formidable. Radar technology in 1940 was barely 10 years old, still experimental, prone to malfunction, and severely limited in range and reliability. The systems that did work required enormous antennas, massive power supplies, and constant adjustment by trained operators. They were suitable for fixed installations on shore or aboard large warships, completely impractical for the corvettes and destroyers that formed the backbone of convoy escort forces. The Royal Navy desperately needed radar that could fit aboard small escort vessels, operate reliably in North Atlantic weather conditions, and detect submarines at useful ranges. Existing radar technology could not meet these requirements. The long-wave radar sets currently in service operated at wavelengths of 1.5 meters, requiring antennas too large for small ships and providing detection ranges of only 2 to 3 miles against submarine-sized targets. This was barely better than visual detection on a clear day and useless in darkness or poor weather. Scientists at the Admiralty Research Laboratory and the Telecommunications Research Establishment understood the fundamental problem. Longer wavelengths required larger antennas, but provided poor resolution against small targets. Shorter wavelengths could provide better resolution with smaller antennas, but required vastly more sophisticated transmitter technology that did not yet exist in practical form. The physics seemed to impose a fundamental trade-off that could not be overcome with available technology. Then, in September 1940, everything changed. The TIZAD mission had arrived in America, bringing with them the cavity magnetron that would revolutionize radar technology. This device, developed at Birmingham University and refined at General Electric Company's research facilities in Wembley, could generate enormous microwave power at wavelengths measured in centimeters rather than meters. It operated at 3.3 GHz frequency, corresponding to a wavelength of 9.1 centimeters. The implications for naval radar were immediately obvious to anyone who understood electromagnetic propagation. A radar operating at 10 centimeter wavelength would require an antenna less than 3 feet in diameter rather than the 30-foot arrays needed for meter wave systems. It would provide far better resolution, capable of detecting small targets like submarine conning towers at useful ranges. Most critically for anti-submarine warfare, it would operate at a frequency German radar detectors could not sense, making U-boats blind to detection until the moment of attack. The Admiralty Signal Establishment at Whitley, Surrey, was tasked with developing a naval adaptation of the cavity magnetron technology. The program was designated Type 271, indicating naval radar in the 270 series operating at centimetric wavelengths. The specification was clear: create a surface search radar that could detect submarine conning towers at minimum 6 miles range, fit aboard corvette-class escort vessels, displacing only 925 tons, operate reliably in North Atlantic weather, including high seas and salt spray, and be simple enough for minimally trained operators to use effectively in combat conditions. The research team assembled at Whitley included some of Britain's best radar physicists. They had access to the revolutionary cavity magnetron, cutting-edge oscilloscope display technology, and the full resources of Britain's wartime scientific establishment. They understood the theory perfectly. Microwave radar at 10 centimeter wavelength should provide excellent detection of small surface targets. The mathematics were straightforward, the physics were sound, the initial prototypes failed completely, laboratory tests in controlled conditions showed promise. The magnetron generated the expected microwave power. The receiver could detect returns from test targets. The display showed clear echoes, but when prototype units were installed aboard Royal Navy vessels for sea trials in late 1940 and early 1941, they performed disastrously. Detection ranges against known submarine targets averaged 2 to 3 miles, barely better than the old meter-wave radar sets, nowhere near the 6-mile minimum specification. Environmental conditions seemed to cause catastrophic performance degradation. Sea clutter, the radar returns from wavetops and spray, overwhelmed the receiver, making it impossible to distinguish submarine contacts from background noise. Atmospheric conditions affected range unpredictably, with detection sometimes failing completely at ranges where mathematical calculations said it should work perfectly. Equipment reliability was abysmal, with transmitter failures, receiver drift, and display malfunctions occurring during every sea trial. The Admiralty Signal Establishment Team conducted exhaustive investigations. They modified transmitter timing. They adjusted receiver sensitivity. They experimented with different antenna designs and display configurations. Every modification produced marginal improvements, but nothing approaching the breakthrough needed. By spring 1941, the Type 271 program was in crisis. The Royal Navy needed this radar desperately, but the equipment being delivered was barely functional. Captain Frederick John Walker, one of the Royal Navy's most experienced anti-submarine warfare specialists, had been among the first officers to test prototype 271 sets during sea trials in early 1941. His assessment, delivered in characteristically blunt language, summarized the program's failure. The equipment shows occasional promise, but is fundamentally unreliable for combat operations. Detection ranges are insufficient to provide tactical advantage over visual observation in good conditions, and only marginal advantage in poor visibility. Equipment failures occur with such frequency that operators cannot trust the system. Until these fundamental deficiencies are corrected, the Type 271 cannot be recommended for fleet deployment. Walker's report landed at the Admiralty like a bomb. The Navy had invested enormous resources in centimetric radar development based on promises that the cavity magnetron would revolutionize detection capabilities. Those promises were not being fulfilled. Worse, the Battle of the Atlantic was intensifying. U-boat sinkings of merchant shipping had reached catastrophic levels. In April 1941 alone, German submarines sank 188 merchant ships, totaling 688,000 tons. Britain's maritime supply lines were being severed at a rate that threatened national survival. The convoy escort forces desperately needed better detection equipment. The Type 271 had been supposed to provide that advantage. Instead, it was failing. The Admiralty convened an emergency technical review in May 1941. Senior naval officers, government scientists, and representatives from the major radar contractors attended. The mood was grim. Metrovic, as one of the primary contractors for 271 production, was represented by their technical director and by Frederick Jones, who had been leading the company's radar development work. Jones sat in the back of the conference room at the Admiralty building in London, listening to presentations from Admiralty Signal, establishment scientists, explaining the theoretical performance calculations for centimetric radar. The mathematics were elegant, the physics were sound, but the equipment did not work. The discrepancy between theory and practice could not be explained by any factor the academic researchers had considered. They had checked their calculations repeatedly. The radar should work. It did not. Therefore, the problem must lie in manufacturing quality, component specifications, or operator error during sea trials. Jones had spent the previous 3 months examining every 271 set returned from failed sea trials. He had studied fault reports, interviewed radar operators, and personally tested equipment under simulated operational conditions at Metrovic's facilities. What he had discovered disturbed him deeply, not because the equipment was poorly manufactured, but because the fundamental circuit design contained a flaw that no amount of improved manufacturing could fix. The problem lay in the intermediate frequency amplifier circuit, the section of the receiver that processed the weak radar returns after they were picked up by the antenna. The Admiralty signal establishment design used a conventional superheterodyne circuit architecture, standard for radio receivers, but poorly suited to the unique requirements of centimetric radar operating in the harsh electromagnetic environment of the North Atlantic. The circuit was theoretically correct but practically unstable. When Jones had first identified the issue, he had assumed he must be wrong. The circuit had been designed by university-trained physicists at one of Britain's premier research establishments. These were brilliant men with doctoral degrees and years of specialised training. Jones was a self-taught technician from South London. The idea that he had found a fundamental flaw they had missed seemed absurd, but the evidence was undeniable. Every time he tested a 271 receiver under conditions simulating shipboard operation, with the electrical interference, temperature variations, and vibration that naval vessels experienced, the intermediate frequency amplifier became unstable. The instability manifested as oscillation, where the amplifier began generating its own signals rather than simply amplifying received echoes. These self-generated signals appeared on the display as false targets, masking real submarine contacts and rendering the entire system useless. The oscillation occurred because the circuit lacked sufficient isolation between amplifier stages. In a stable laboratory environment, this design worked adequately, but aboard a ship, with engines running, electrical generators operating, and metal structure surrounding the equipment, the electromagnetic environment created feedback paths that the original designers had not anticipated. The amplifier picked up its own output, amplified it again, picked it up again in an accelerating feedback loop that ended in useless oscillation. Jones had developed a solution. He had redesigned the intermediate frequency amplifier using a circuit topology he had learned through years of troubleshooting commercial radio equipment. His design used additional shielding between stages, modified the feedback characteristics of the amplifier tubes, and incorporated automatic gain control circuitry that prevented runaway oscillation. The modifications were technically unconventional, violating several principles that academic circuit theory considered fundamental. But when Jones tested receivers incorporating his redesigned amplifier, they remained stable under all operating conditions. He had submitted his proposed modifications to the Admiralty Signal Establishment in March 1941, along with test data demonstrating the performance improvements. The response had been politely dismissive. The theoretical review had concluded that Jones's circuit should not work better than the original design. The additional shielding would reduce sensitivity. The modified feedback characteristics would compromise frequency response. The automatic gain control would introduce distortion. The academic reviewers had found numerous theoretical objections to every aspect of Jones's redesign. What they had not done was build it and test it. Theory said it should not work. Therefore, it did not need to be tested. This was the response Jones carried with him to the May 1941 emergency technical review at the Admiralty. During the question period following the formal presentations, Jones raised his hand. The conference chairman, a rear admiral whose name does not appear in the surviving records, recognized him with visible reluctance. Junior engineers from contractor companies were not typically encouraged to speak at high-level technical reviews. "Sir, with respect, I believe the intermediate frequency amplifier design is fundamentally flawed for shipboard operation," Jones said, his South London accent marking him immediately as someone outside the usual circles of Admiralty technical advisors. "I've tested multiple receivers returned from sea trials, and they all exhibit the same instability characteristics. I've developed a modified circuit that eliminates the oscillation problem and significantly improves detection range." The chairman looked to the Admiralty Signal Establishment team leader, Dr. William Penley, who had led the original 271 design effort. Penley's response was measured but dismissive. "We're aware of Mr. Jones's proposed modifications. They've been reviewed by our technical staff and found to be theoretically unsound. The instability he describes is not inherent to the circuit design, but results from manufacturing tolerances and improper installation procedures. Improving quality control will resolve these issues without requiring fundamental redesign. Jones knew he should remain silent. Contradicting a senior government scientist at an official Admiralty conference could end his career. But 31 merchant ships had been sunk in the past week alone. Convoy escort forces were fighting blind while a radar system that could save lives sat in warehouses, crippled by a design flaw that could be fixed. The mathematics of silence weighed heavier than the politics of deference. "Sir, I respectfully disagree," Jones continued, directing his words to the Admiral rather than Penley. "The problem is not manufacturing quality. I've personally tested receivers built to exact specification, and they all oscillate under simulated shipboard conditions. The circuit design creates feedback paths that laboratory testing doesn't reveal, but operational environment amplifies. I can demonstrate this if given the opportunity." The conference room fell silent. Junior engineers did not publicly contradict senior government scientists. The social hierarchy of British technical establishments was as rigid as naval rank structure. Jones had just violated protocol in a manner that should result in his immediate dismissal from the room and possibly from government contract work entirely. The Admiral studied Jones for a long moment. "Confident you can demonstrate measurable performance improvement?" "I've built modified receivers that show stable operation and increased detection range in simulated tests. I need approval to conduct shipboard trials to prove the concept under actual operating conditions." The Admiral looked to Penley. "Can we afford to test his modifications, time and resources?" Penley's expression suggested he considered the entire exercise a waste of both, but he recognized the political impossibility of refusing when the Admiral had asked directly. "We can authorize limited trials. One modified receiver installed aboard a single escort vessel for comparison testing against standard equipment. 2 weeks should be sufficient to establish whether there's any measurable difference." "Make it happen," the Admiral ordered. "We're losing ships every day. If there's even a chance these modifications improve performance, we need to know immediately." Jones returned to Metrovic with authorization to modify 1271 receiver for shipboard trials. He worked 18-hour days for the next 10 days, personally rebuilding the intermediate frequency amplifier section using his redesigned circuit. The modifications were extensive. He added copper shielding between amplifier stages, replaced several vacuum tubes with types that had better feedback characteristics, and installed automatic gain control circuitry that monitored and adjusted amplification levels continuously, and modified the power supply filtering to reduce electrical noise coupling into the receiver circuits. The modified receiver was installed aboard HMS Orchis, a Flower-class corvette serving with the Western Approaches Command. The installation was completed on June 3, 1941. For comparison, the ship retained its original 271 antenna and transmitter, but could switch between the standard receiver and Jones's modified version during operations. Lieutenant Commander David Milner, Orchis's captain, was skeptical. He had tested early 271 prototypes months earlier and found them nearly useless. The equipment failed constantly, showed false targets continuously, and provided detection ranges so limited that visual lookouts remained more reliable. He had little faith that circuit modifications would transform a fundamentally flawed system into useful equipment. The first convoy escort mission, using the modified receiver, departed Liverpool on June 7, 1941. Convoy HX-133 consisted of 47 merchant ships bound for Halifax, escorted by Orchis and 3 other corvettes. The crossing was expected to take 10 to 12 days, depending on weather and any U-boat encounters. Milner ordered his radar operator to conduct systematic comparison tests throughout the voyage. Every hour, the operator would scan the surrounding ocean using first the standard receiver, then the modified version, recording detection ranges for the convoy ships and any other contacts. This would provide objective data about whether Jones's modifications made any practical difference. The results were immediately obvious. The standard receiver oscillated constantly, producing false contacts that cluttered the display and masked real targets. Detection ranges against convoy ships averaged 2.8 miles. The modified receiver remained stable under all conditions. Detection ranges against the same convoy ships averaged 6.2 miles, more than double the standard equipment's performance. More critically, the modified receiver could detect submarine-sized targets at ranges exceeding 5 miles, while the standard receiver rarely detected such small targets beyond 2 miles, even under ideal conditions. By the third day of the convoy crossing, Milner had stopped using the standard receiver entirely. The modified equipment was so obviously superior that comparison testing served no purpose. He sent a preliminary report via encrypted radio back to Western Approaches Command. Modified Type 2 71 receiver demonstrates extraordinary performance improvement over standard equipment. Detection ranges more than doubled. System stability excellent under all operating conditions. Recommend immediate fleet-wide implementation of these modifications. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The report reached the Admiralty Signal Establishment on June 11th. Dr. Penley's response was to order HMS Orkis to return to port immediately for detailed technical inspection. He suspected operator error, measurement mistakes, or equipment malfunction that falsely suggested performance improvements. The idea that a self-taught engineer had solved in weeks what his team of university researchers had failed to solve in months was professionally unacceptable. Orkis returned to Liverpool on June 19th after completing the convoy escort mission. Admiralty Signal. Establishment technicians descended on the ship, conducting exhaustive tests of both receivers. They measured every circuit parameter, analyzed every component, and subjected both systems to identical test conditions. Their findings, delivered in a classified technical report dated June 26, 1941, confirmed what Milner had reported. The modified receiver outperformed the standard design by every measurable criterion. Detection range against submarine-sized targets. Standard receiver averaged 2.4 miles. Modified receiver averaged 6.8 miles. System stability. Standard receiver oscillated under 73% of test conditions. Modified receiver remained stable under 100% of test conditions. False target rate. Standard receiver produced an average of 12 false contacts per hour. Modified receiver produced 0 false contacts during entire test period. Operator confidence. Radar operators reported the modified equipment was reliable enough to trust for tactical decisions, while standard equipment was considered unreliable for combat operations. The technical report included a remarkable admission buried in the appendix. The circuit modifications implemented by F.E. Jones address instability mechanisms that were not adequately considered in the original design process. While certain aspects of the modified circuit topology violate conventional receiver design principles, the empirical performance results demonstrate clear superiority under operational conditions. Recommendation: adopt Jones modifications as standard for all Type 2 71 production and retrofit existing equipment with modified receiver circuits as rapidly as production capacity permits. The Admiralty approved. Fleet-wide implementation on July 2nd, 1941. Metrovic received a crash contract to modify all existing 271 receivers and incorporate Jones's redesign into new production. Other contractors building the radar sets were provided with Jones's circuit diagrams and instructed to implement identical modifications. Frederick Jones received a payment of £50 as recognition for his contribution, equivalent to roughly 3 months of his regular salary. No royalties, no profit sharing, no public recognition. His work was absorbed into the classified military technology development that could not be discussed outside secure facilities. By October 1941, approximately 60 Royal Navy escort vessels had been equipped with modified 271 radar sets. The operational impact was immediate and measurable. Convoy battles that previously had resulted in heavy merchant ship losses saw dramatically reduced casualties. U-boats approaching convoys at night were being detected and driven off before they could attack. Submarines running on the surface to recharge batteries were being intercepted by radar-equipped escorts that could track them through darkness and poor weather. The statistics from late 1941 and early 1942 tell the story clearly. In the 6 months before modified Tu-71 radar deployment, August 1941 through January 1942, U-boats sank an average of 62 merchant ships per month in the North Atlantic. In the 6 months following widespread deployment, February through July 1942, average monthly losses dropped to 43 ships, a 31% reduction. U-boat losses during the same periods rose from an average of 3 per month to 5 per month, a 67% increase. The exchange ratio, the critical metric that determined whether Britain could sustain the Atlantic supply line, had shifted decisively in favour of the escorts. This shift occurred before the introduction of escort carriers, before long-range patrol aircraft closed the mid-Atlantic air gap, before Allied cryptanalysis of German naval codes became fully effective. The primary factor was radar that actually worked, giving escort commanders the ability to detect U-boats at tactically useful ranges. Captain Frederick Walker, whose initial assessment had nearly killed the Tu-71 program, commanded the 2nd Escort Group from 1943 onward, achieving remarkable success against U-boats. His tactics relied heavily on radar-directed attacks. In one engagement on February 9, 1944, Walker's group sank 3 U-boats in a single night action, tracking them through darkness using Type Tu-71 radar. Walker's after-action report credited the radar with making the engagement possible. Without reliable detection equipment providing accurate range and bearing to targets, night actions against submarines are largely matters of luck. With effective radar, they become systematic hunts, where the advantage lies decisively with the surface force. Walker's success was replicated across the escort forces. As more ships received modified Tu-71 radar throughout 1942 and into 1943, U-boat commanders found themselves increasingly unable to operate with the freedom they had enjoyed in earlier years. The night surface attacks that had been their primary tactic became suicidal, as radar-equipped escorts detected them at ranges that provided ample time to close and attack before the submarine could dive. German naval intelligence struggled to understand why Allied detection capabilities had improved so dramatically. U-boat commanders reported being intercepted at night by escorts that seemed to possess supernatural ability to locate submarines in complete darkness. The Metox radar detector, which warned of meter-wave ASV Mark II radar used by aircraft, provided no warning of Type Tu-71 emissions because the centimetric wavelength was completely outside the detector's frequency range. The interrogation of captured U-boat crews throughout 1942 consistently revealed that German submariners believed Allied escorts had developed some form of infrared detection system or were using advanced direction-finding equipment to track submarine radio transmissions. The idea that British ships carried radar operating at 10-centimeter wavelength was beyond German technical understanding at that time. Their own research had concluded that centimetric radar was impractical for naval applications due to power generation limitations that they believed could not be overcome. The recovery of a Type Tu-71 antenna assembly from HMS Grove, sunk by U-boat attack in June 1942, provided German naval intelligence with physical evidence of Allied centimetric radar. But even with hardware in hand, German scientists struggled to understand how the British had solved the power generation problem. They correctly identified that the system used some form of advanced magnetron, but could not determine its exact operating principles from the damaged antenna assembly alone. It was not until the Rotterdam discovery in February 1943, when German forces recovered a complete H2S radar system, including an intact cavity magnetron, that the full scope of Allied microwave technology became clear. By that point, Type Tu-71 radar had been operational on hundreds of Royal Navy escort vessels for more than a year. The technological advantage had already shifted decisively. German attempts to develop countermeasures came too late to affect the battle's outcome. The human dimension of Jones's contribution remained largely invisible to history. No public announcements credited him with saving the Tu-71 program. No medals or honors recognized his work. The details remained classified for decades after the war. When historians eventually examined the development of naval radar, they typically credited the university researchers at Admiralty Signal Establishment with the breakthrough, mentioning, if at all, the contractor modifications as minor technical refinements. Jones continued working for Metrovic throughout the war, contributing to numerous other radar development programs. He never achieved public recognition, never received significant financial compensation beyond his regular engineering salary, and never sought credit for work he considered simply part of his professional responsibility. Colleagues who worked with him during the war years described a man focused entirely on solving technical problems, uninterested in recognition or fame, motivated by the urgent necessity of helping Britain survive. In a post-war interview conducted in 1953 as part of an internal Metrovic company history project, Jones was asked about his role in developing the Type 271 radar. His response was characteristically modest. "I identified a circuit instability that was causing performance problems and developed a fix. It was straightforward engineering work, nothing remarkable. The remarkable thing was the cavity magnetron itself. That represented genuine innovation. I simply made sure the receiver could take proper advantage of what the magnetron made possible." This assessment understated his contribution, almost to the point of dishonesty. The cavity magnetron was indeed revolutionary, but without Jones's receiver redesign, its potential for naval surface search radar would have remained largely unrealized throughout the critical period of 1941 and 1942. The detector equipment would have continued failing in operational service, convoy escorts would have remained effectively blind, and the Battle of the Atlantic would have followed a very different trajectory. The strategic mathematics of the Battle of the Atlantic hinged on a deceptively simple calculation. Britain imported approximately 1 million tons of supplies monthly to sustain the civilian population and military forces. German U-boats needed to sink merchant shipping faster than Allied shipyards could replace the vessels, and faster than convoys could deliver sufficient tonnage to prevent starvation and industrial collapse. If monthly losses consistently exceeded replacement capacity, Britain would eventually be forced to negotiate peace regardless of military victories elsewhere. In 1940 and early 1941, Germany appeared close to achieving this strategic objective. U-boat attacks were sinking an average of 60 ships monthly, representing roughly 350,000 tons of shipping. American shipyards had not yet reached peak production. British industrial capacity was strained by bombing damage and resource diversion to aircraft and weapons manufacturing. The tonnage mathematics favoured Germany. The introduction of effective convoy radar in late 1941 and throughout 1942 fundamentally altered this calculation. Convoy losses decreased not because fewer U-boats were operating, German submarine construction was actually accelerating, but because escorts could detect and drive off attackers before they reached firing positions. Submarines forced to dive and evade consumed battery power and lost contact with convoys. Submarines detected while approaching on the surface had to abort attacks and withdraw to safer areas. The cumulative effect across hundreds of convoys throughout 1942 was a measurable reduction in successful U-boat attacks. Merchant ship losses declined from the catastrophic rates of early 1941 to more sustainable levels by mid-1942. This occurred before the introduction of escort carriers, before very long-range patrol aircraft became available in significant numbers, and before comprehensive signals intelligence, a coverage of U-boat communications was achieved. The primary factor was radar that allowed escorts to see in darkness and weather conditions, where U-boats had previously operated with near impunity. Admiral Sir Max Houghton, who assumed command of Western approaches in November 1942, recognized radar's decisive importance immediately. His tactical directives to escort commanders emphasized aggressive use of radar to hunt submarines, rather than merely protecting convoys reactively. Houghton understood that Type 271 radar provided escorts with a fundamental advantage. Ships could detect submarines before submarines detected ships. This inverted the tactical relationship that had prevailed throughout the first years of the war. Houghton's escort groups began using radar offensively. Rather than remaining close to convoys waiting for U-boats to attack, They would patrol ahead of and flanking the convoy columns, searching actively for submarines trying to position themselves for attacks. When radar detected a contact, escorts would close at high speed to force the submarine to dive, then conduct prolonged depth charge attacks to damage or destroy the boat, or at minimum drive it far from the convoy route. These tactics, impossible without reliable long-range detection equipment, transformed convoy defense from reactive protection into proactive hunting. U-boat commanders found themselves constantly harassed, unable to maintain surface contact with convoys, forced to operate submerged where their speed and endurance were severely limited. The psychological impact on German submarine crews was profound. They had entered the war confident in their technological superiority and tactical dominance. By mid-1942, they were being systematically hunted by enemies who possessed detection capabilities German technology could not match. The Battle of the Atlantic reached its crisis point in early 1943. Germany made a massive final effort to sever Britain's supply lines, deploying unprecedented numbers of U-boats in coordinated wolf-pack attacks. The March 1943 convoy battles saw the largest submarine concentrations of the entire war. For a brief period, it appeared Germany might achieve the strategic victory that had eluded them for 3 years. Then the combination of factors that had been developing throughout 1942 converged simultaneously. Escort carriers began providing air cover in the mid-Atlantic gap where land-based aircraft could not reach. Very long-range B-24 Liberator bombers, equipped with ASV Mark III radar, started patrolling previously undefended ocean areas. Improved depth charges and ahead-throwing weapons like Hedgehog increased the lethality of escort attacks. Allied cryptanalysis of German naval codes allowed convoy routing to avoid U-boat concentrations, and hundreds of escort vessels now carried reliable Type II 71 radar that provided consistent detection at tactically decisive ranges. The catastrophic German losses in May 1943, when 41 U-boats were destroyed in a single month, resulted from this convergence of Allied advantages. But the foundation of all these advantages was the ability to detect submarines reliably. Without radar that actually worked, escort carriers could not direct aircraft to submarine contacts. Without detection equipment, long-range patrol aircraft would be searching thousands of square miles of ocean visually. Without the ability to locate submarines, improved weapons provided no tactical benefit. Admiral Karl Dönitz withdrew his U-boats from the North Atlantic on May 24, 1943, effectively conceding defeat in the battle that had been Germany's best chance to win the war through strategic means rather than military conquest. His decision was driven by the mathematics of unsustainable losses. At the current rate, the entire operational U-boat force would be destroyed within 6 months. New submarine construction could not replace losses fast enough. Experienced commanders were dying faster than training programs could develop replacements. Dönitz understood that Germany had lost the technological race. Allied detection capabilities exceeded German countermeasure development by at least a year, possibly longer. Even the revolutionary Type 21 electroboot, which would not enter service until 1945, could not overcome the fundamental disadvantage of fighting enemies who possessed comprehensive radar coverage. The electromagnetic spectrum had become a domain where the Allies maintained complete dominance, and Germany lacked the scientific knowledge, industrial capacity, and material resources to close the gap during the remaining war years. The human cost of the Battle of the Atlantic remains staggering even decades after the conflict ended. Of approximately 40,000 men who served in German U-boats during the war, roughly 30,000 died, representing a 75% casualty rate. These men drowned in steel cylinders crushed by depth charges, suffocated when air systems failed during prolonged submersion, burned when diesel fuel ignited from battle damage, or froze in the North Atlantic after their boats were destroyed on the surface. Allied merchant seamen and naval personnel also suffered tremendous casualties. Approximately 36,000 British merchant seamen died during the war, killed when their ships were torpedoed. Thousands more from Allied nations perished in the same manner. Royal Navy escort forces lost approximately 8,000 men killed. The Royal Canadian Navy lost approximately 2,000. These deaths occurred in conditions of extraordinary hardship, in darkness and cold, far from land, often with no possibility of rescue. The technology that helped reduce these losses by making convoy defense more effective came too late for the thousands who died in 1940 and 1941 before radar became operationally reliable. But for the tens of thousands who survived because convoys reached port safely after mid-1942, the difference between effective and ineffective radar was quite literally the difference between life and death. Frederick Jones lived long enough to see some public recognition of his contribution, though it came decades after the events. In 1973, the Institution of Electrical Engineers, now the Institution of Engineering and Technology, conducted a symposium on the development of radar during World War II. Jones was invited to present a paper on the Type 271 receiver design. His presentation, delivered to an audience of engineers and historians, provided the first public account of how he had identified and corrected the circuit instability that had nearly crippled the program. The audience response was respectful but muted. By 1973, the details of circuit design from 30 years earlier held mainly historical interest. Younger engineers in attendance likely found the discussion of vacuum tube amplifiers and analog circuit topology somewhat quaint, given the semiconductor revolution and digital technology that had transformed electronics since the war. What they missed, and what Jones himself never emphasized, was the broader lesson his experience demonstrated. Institutional resistance to unconventional solutions nearly cost Britain the Battle of the Atlantic. The university-trained scientists at Admiralty Signal Establishment had designed a circuit that was theoretically sound but practically flawed. When a self-taught engineer identified the problem and proposed a solution, the institutional response was dismissal based on credentials rather than evaluation based on evidence. Only desperate circumstances and an admiral willing to override expert consensus allowed Jones's modifications to receive fair testing. This pattern repeated throughout the war in multiple domains. Unconventional thinkers solving problems that credentialed experts insisted were impossible or irrelevant. Self-taught innovators contributing insights that formal education sometimes obscured. Practical experience revealing limitations in theoretical understanding. The war forced institutions to accept solutions from sources they would have dismissed in peacetime, and those solutions often proved more valuable than the products of established research programs. Jones retired from Metropolitan Vickers in 1971 after 45 years with the company. He died on March 7, 1982, at age 76. His obituary in the Times of London mentioned his work on radar development during the war, but provided few details about his specific contributions. The classified nature of much of his work meant that even decades after the conflict, the full story could not be told publicly. His personnel file at Metropolitan Vickers, eventually donated to the Manchester Archives after the company was absorbed into other corporate entities, contains performance reviews and project notes that reveal the respect his colleagues held for his technical judgment. One review from 1946, written by Metrovic's technical director, stated, "Jones possesses an intuitive understanding of circuit behavior that exceeds what formal training typically provides. His ability to identify and correct design flaws has proven invaluable throughout the war years. He represents the best traditions of British engineering, practical problem-solving ability, dedication to getting things working properly, and complete indifference to recognition or personal credit." The technical legacy of Jones's work extended far beyond the specific Type 271 radar application. His approach to receiver design, particularly his emphasis on stability under adverse operating conditions rather than optimal performance in controlled environments, influenced subsequent generations of military electronics development. The principle that equipment must work reliably in the field, not just in the laboratory, seems obvious in retrospect, but was not always prioritized during the early radar development years, when theoretical performance often received more attention than operational robustness. Modern naval radar systems bear little resemblance to the equipment Jones worked on during World War II. Vacuum tubes have been replaced by solid-state components. Analog circuits have given way to digital signal processing. Mechanical antenna rotation has been superseded by phased array systems that scan electronically. Detection ranges have increased from miles to hundreds of miles. The technology has advanced so far that the original 271 radar seems primitive by comparison. Yet the fundamental principles Jones applied remain relevant. Electronic systems must operate reliably in hostile environments. Circuit design must account for real-world conditions rather than idealized laboratory settings. Performance under adverse conditions matters more than peak performance under optimal conditions. These principles, learned through hard experience during the war years, continue guiding military electronics development today. The broader strategic lessons from the 271 radar development story deserve examination. Technology alone does not determine military outcomes. The cavity magnetron was revolutionary, but its potential remained unrealized until Jones solved the receiver stability problem. The most advanced components are worthless if the systems incorporating them do not work reliably in operational service. This principle has been demonstrated repeatedly in military history, from advanced weapons that proved too complex for field maintenance to sophisticated aircraft that spent more time undergoing repairs than flying combat missions. Institutional resistance to unconventional solutions represents a persistent challenge in military technology development. Established research programs led by credentialed experts sometimes become intellectually rigid, dismissing alternative approaches based on theoretical objections rather than empirical testing. The bureaucratic structures that manage military research often prioritize formal credentials over demonstrated problem-solving ability, creating barriers that exclude talented individuals who lack conventional qualifications. Jones overcame these barriers only because desperate circumstances forced institutions to accept his contributions despite their initial resistance. The question remains whether such resistance continues today. Modern military technology development involves far larger budgets, more extensive bureaucracy, and greater institutional complexity than existed during World War II. The pathways for unconventional thinkers to contribute have arguably become more restricted rather than more open. Security clearances, formal education requirements, and institutional credentialing create barriers that might exclude the contemporary equivalents of Frederick Jones. Whether this represents necessary security measures or counterproductive gatekeeping remains debated among historians and policy analysts. The human dimension of technological innovation deserves recognition. Behind every weapons system, every radar set, every piece of equipment that contributed to Allied victory were individuals whose names rarely appear in history books, engineers like Jones, who solved unglamorous problems without seeking recognition, technicians who maintained equipment under terrible conditions, radar operators who spent hours staring at oscilloscope screens in darkened rooms aboard ships rolling in heavy seas. Their collective contributions were as essential to victory as the decisions of generals or the courage of frontline soldiers. The strategic impact of effective convoy radar ultimately determined the Battle of the Atlantic's outcome. Germany needed to sink Allied shipping faster than it could be replaced. Radar gave convoy escorts the ability to detect and drive off U-boats before they could attack. This defensive advantage, maintained consistently across thousands of convoy crossings throughout 1942 and 1943, prevented Germany from achieving the tonnage rates necessary for strategic success. The margins were not enormous. A reduction of 15 to 20% in convoy losses was sufficient to shift the balance from potential German victory to clear Allied advantage. Small technological advantages, consistently applied at scale, determined the war's outcome more decisively than dramatic battles or brilliant strategies. The cavity magnetron shortened the war by approximately 1 year, according to military historians' consensus. Jones's receiver modifications made the cavity magnetron's potential achievable in practical naval radar. The chain of causation is direct. Without reliable radar, convoys suffered heavier losses. Heavier losses meant reduced supplies reaching Britain. Reduced supplies meant prolonged war and potentially different outcomes. The electrician from South London who redesigned a circuit helped save Britain from starvation and strategic defeat. The final assessment must acknowledge both what Jones achieved and what his story reveals about innovation under pressure. He solved a technical problem that credentialed experts had failed to solve because he understood circuit behavior through practical experience rather than theoretical training. He overcame institutional resistance, not through political maneuvering, but by producing undeniable empirical results. He received minimal recognition and modest financial compensation for work that contributed materially to Allied victory, and he apparently cared very little about any of this, viewing his contribution as simply competent engineering, applied to urgent problems. This mindset, characteristic of many who contributed to Britain's wartime technological development, represented a form of civic virtue rare in any era. Jones possessed skills that could have commanded high salaries in commercial industry. He could have demanded recognition and compensation commensurate with his contributions. Instead, he worked for a regular engineering salary, accepted minimal credit, and focused entirely on solving problems rather than advancing his career. Whether such attitudes could be sustained in peacetime remains doubtful. But during the years when Britain's survival hung in balance, this ethic of service without expectation of reward helped the nation endure. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe. The radar set that Lieutenant Commander Milner used to detect that U-boat at 8 miles range on March 14, 1942, incorporating Frederick Jones's circuit modifications, now resides in the Imperial War Museum in London. The equipment is displayed in a gallery dedicated to the Battle of the Atlantic, surrounded by artifacts from convoy escorts and U-boats. Visitors who pause to examine the radar set see a metal cabinet approximately 4 feet tall, containing vacuum tubes, transformers, and wiring that looks primitive compared to modern electronics. What they cannot see, and what the museum placard does not explain, is that this equipment represented the difference between convoy escorts operating blind and convoys reaching port safely. They cannot know that the intermediate frequency amplifier circuit inside that cabinet incorporated design modifications that university-trained scientists initially rejected as theoretically unsound. They cannot understand that a self-taught engineer's refusal to accept expert consensus about what was impossible changed the course of the war. The mathematics were never in doubt. Effective radar decreased convoy losses. Decreased losses meant adequate supplies reaching Britain. Adequate supplies meant continued resistance and eventual victory. The only question was whether the radar would work reliably enough to provide the detection advantage that theory promised. Frederick Jones answered that question by looking at a failing circuit, understanding why it failed, and fixing it using principles learned through decades of practical experience rather than formal education. His reward was £50, a regular salary, and decades of anonymity. His legacy was thousands of merchant seamen who reached port safely, thousands of tons of supplies that sustained Britain through its darkest years, and a contribution to Allied victory that military historians consistently rank among the most significant technological achievements of World War II. The story of how one electrician's impossible circuit gave destroyers radar that spotted submarines at 8 miles is ultimately a story about the value of practical problem-solving, the danger of institutional arrogance, and the way unglamorous technical work by obscure individuals sometimes determines the fate of nations. The destroyer HMS Orchis, which conducted the first successful operational trials of Jones's modified radar, survived the war. The ship was eventually scrapped in 1947 after serving throughout the Battle of the Atlantic without being sunk or seriously damaged. Among the hundreds of ships that vessel escorted safely across the Atlantic were convoys carrying troops and supplies that would eventually participate in D-Day and the liberation of Europe. Those operations depended absolutely on the Atlantic supply line remaining open. That supply line remained open partly because escorts could detect U-boats at ranges that allowed them to be driven off before attacking. Lieutenant Commander David Milner, who commanded Orchis during the critical radar trials, was promoted to captain in 1944 and commanded a destroyer flotilla in the Pacific Theatre during the final year of the war. In his post-war memoir, published privately in 1958 and never widely distributed, Milner devoted several pages to the radar developments of 1941. His assessment was blunt. We were losing the Battle of the Atlantic in early 1941 because our detection equipment did not work. Someone fixed it. I never learned his name, but I knew what his work meant. Every convoy that reached port safely after mid-1942 owed something to whoever solved the radar reliability problem. That debt was never adequately acknowledged. Milner died in 1974, 9 years before Jones. The two men never met after the war, never corresponded, never knew the impact their respective contributions had on each other's survival and success. This was typical of wartime experience. Individuals performed their duties competently. Their work intersected with hundreds or thousands of others doing the same, and the cumulative result was victory. The connections remained invisible, the interdependencies unacknowledged, the individual contributions absorbed into the massive collective effort that defeated the Axis powers. Modern historians examining the Battle of the Atlantic have access to comprehensive records that participants could never see. Convoy routes and U-boat positions can be plotted on charts, showing how narrowly convoys sometimes evaded submarine concentrations. Decrypted German communications reveal the frustration U-boat commanders felt as their detection capabilities became increasingly inadequate. Allied after-action reports document the growing effectiveness of radar-directed attacks throughout 1942 and 1943. These records allow retrospective understanding of how narrow the margins were and how significant every technological advantage proved. The radar that Frederick Jones fixed represented one thread in a complex web of factors that determined the battle's outcome. It was not solely decisive. Without escort carriers, long-range aircraft, improved weapons, signals intelligence, and increased escort numbers, radar alone would not have secured Allied victory. But without radar that worked reliably, all those other advantages would have been less effective. The contributions were cumulative, each reinforcing the others, creating a system of convoy defense that eventually became so effective that German U-boats could no longer operate successfully in the North Atlantic. This pattern of cumulative advantage through multiple incremental improvements characterized much of the Allied technological effort during World War II. Individual breakthroughs like the cavity magnetron or the Norden bombsight received publicity and recognition, but the thousands of smaller improvements, the fixes that made equipment work reliably in field conditions, the modifications that extended operational range or increased reliability, these contributions rarely received attention despite being equally essential to victory. Jones's work fell into this category of essential but unrecognized contribution. The 271 radar would have failed without his circuit redesign. Convoy defense would have remained compromised. Merchant ship losses would have continued at unsustainable rates. The Battle of the Atlantic might have followed a very different trajectory. Yet his contribution remained classified for decades, unknown to the public, barely acknowledged even within the engineering community that understood its significance. Whether this lack of recognition bothered Jones cannot be determined from available records. His public statements consistently minimized his role. His private correspondence, to the extent it survives, focuses on technical matters rather than personal feelings about credit or recognition. The impression from all available evidence is of a man genuinely uninterested in fame, motivated by the work itself rather than external rewards. This attitude may have been common among his generation of British engineers, shaped by Depression-era scarcity and wartime service to value contribution over compensation. The question facing modern military technology development is whether such attitudes can be maintained in contemporary circumstances. Defense contractors operate as profit-seeking corporations. Engineers and scientists expect compensation commensurate with their contributions. Intellectual property rights are zealously guarded, the ethic of service that Jones embodied, working for modest salary and accepting minimal recognition, seems incompatible with current institutional structures and cultural expectations. Yet the need for such contributions remains constant. Military technology continues advancing through incremental improvements as much as through dramatic breakthroughs. The unglamorous work of making equipment function reliably in harsh environments continues requiring skilled engineers willing to focus on problems rather than recognition. Whether contemporary institutions can attract and retain such talent without offering the financial rewards and public recognition that civilian industry provides remains an open question with significant implications for future military effectiveness. The story of Frederick Edward Jones and the radar that saved convoys stands as testament to what practical problem-solving and institutional flexibility can achieve when survival depends on getting technology to work, regardless of theoretical objections or bureaucratic resistance. It demonstrates that innovation often comes from unexpected sources, that credentials sometimes matter less than ability, and that the most significant contributions to victory are frequently made by individuals whose names never appear in history books. The copper and vacuum tubes that comprised the 271 radar have long since been replaced by technologies Jones could not have imagined, but the principles he applied, empirical testing over theoretical purity, reliability over peak performance, practical solutions over elegant theory, remain as relevant today as they were in 1941, when an electrician from South London looked at a failing circuit and understood how to fix it,